In Chapter 16, we discuss waves. Like this traveling wave we see here, this one has a sinusoidal shape. We'll start simpler with just a traveling pulse, a wave pulse. And basically, we want to look at two things. We want to know how to mathematically describe it, and then we want to understand the forces, the mechanism behind why a wave exists. So let's start with a wave pulse. And I just want to sketch it. This is just going to be a snapshot of this wave pulse at t equals 0. And let's say it starts from the origin. And it's going to travel down at a speed v to the right. This graph that I've drawn is a graph along the x-axis. It's not a function of time. That's not what I'm drawing here. The function of x. And the wave is a pulse in the y direction. So this is just a snapshot at t equals 0. So what I've drawn here is just y. It's a function of x, but I've set t equal to 0. What I'd like to know is, if I know the shape at t equals 0, I also know the shape at any time. It's just that it moves forwards along the x-axis. So how do I describe that? So now I want to draw it at some later time, not necessarily equal to 0. And I'd like to know what it looks like now. It's a function of x and it's a function of time, but it turns out I'll be able to write it in a simple form. So let's draw what it looks like to get a clue. So now it's exactly the same shape, I'm assuming. Some waves distort their shape as they travel, and that effect is called dispersion. We're ignoring that right now. No change in the pulse's shape at all, I'm assuming. All that happens is now the center of the wave advances. And so the pulse is now further down the x-axis, like over here. Precisely the same shape, it just moved ahead. So for example, suppose I want to know at some position x on the x-axis, what the y value is of that point. Given that I know what it was at t equals 0. Well, all I have to do is look back to the left. This is the same wave, but at a time t later. And to figure out what the y value is of that point, all I need to do is just look ahead a little bit. Look back a little bit. A distance vt. You see, this point right here is exactly the same y value as this one. The only difference is I have to look back by a distance minus vt. That's what happens when the pulse doesn't lose any shape. All I have to do is look back to see what the y value is. So in other words, I just take exactly the same function as at t equals 0, but I replace x with x minus vt. So this is just equal to y of x minus vt, comma 0. So that's very interesting. It means that the wave function, the function that describes the wave, it is a function of x and t, but not as separate variables. They will always appear together in the combination x minus vt. This means that all wave functions, at least the ones that don't change their shape as they travel, all wave functions obey that rule. So let's summarize it this way. All wave functions, they're all functions of x and t, but they only depend on x and t in a certain combination. In this case, it was x minus vt. What if the pulse was traveling instead to the left? Well, then you'd have to look to the right to find the right y value. And that means that waves traveling to the right involve x minus vt. If they travel to the left, it would be x plus vt. So we'll write it this way, x minus or plus vt, depending on the direction of travel. You would use a minus sign for right moving, and you have to use a plus sign if they're left moving waves. Notice carefully negative if they're traveling in the positive x direction, so it might sound backwards, but if you understand the argument, then it's clear. Okay, so that's how wave functions look. They depend on the combination x minus or plus vt. Now we can also see that since they involve x and t in that way, wave functions obey a special equation. I don't mean the equation is of this form, I mean they obey a certain equation. It's called the wave equation. This is a wave function. The wave equation says that if I take the second derivative of the function with respect to time. Now, notice it depends on two variables, x and t. So when I say take the derivative with respect to time, it means I'm taking a partial derivative. So the second derivative of y with respect to time, and those are partial derivatives. If I take the second time derivative, every time I take one of those derivatives, notice it'll pull out a factor of v, the constant speed in front of the function. So since it depends on x and t like this, taking derivatives with respect to x of this function, basically the same as taking derivatives with respect to time. The only difference is the time derivatives pull out a factor of v. So taking two time derivatives will pull out v squared, and you'd get the same thing as taking two derivatives with respect to x. And that's called the wave equation. It's not the wave function itself, it's an equation that the wave function obeys. That wave equation is extremely important because it gives a clue as to the mechanism behind a wave. Why does a wave exist? The clue is this involves a second derivative with respect to time. What is that? Now think physics. What's the second derivative of position versus time? Acceleration. So the left-hand side here has to do with the acceleration of, let's say, the string that's carrying the wave. Let's look back at the wave for a second. Notice that the string itself only moves up and down. That's why it's called a transverse wave, because the motion is sideways. The string itself is not actually moving to the right. The string is actually moving up and down. So the string is vibrating up and down. It's accelerating up and down. And let's think about physics and forces for a second. When is the string going to be pulled hardest, say downwards? Well, look, it's going to be pulled hardest downwards when its neighbors are both angled in such a way that the tension in the string pulls it down. That's going to happen when the string is curved the most. I'm watching this red marked piece of the string. When does it feel the most downwards force? It's when its neighbors are pulling it downwards on both sides. When it's curved the most strongly is when that piece of string is going to feel the greatest downward force. So it's giving us a clue as to how the physics of this wave works. The string will accelerate downwards when it's curved downwards. Okay, let's go look back at this wave equation. The acceleration depends on the curvature. Remember that the second derivative with respect to x would be, that's a measure of how concave down, up or down the string is, and that's just how curved it is. So in fact, we can use Newton's law for the string. Newton's law for the string is going to say, take the mass times acceleration of a tiny portion of the string, and that must be equal to the net force on that portion of the string. So mass times acceleration, actually it'll be the mass density, not m, but mu. Mu is the mass per meter on the string. mu, is the linear mass density. Measured in kilograms per meter. So Newton's law is going to say take the mass density times the acceleration. That's just ma, basically. Ma equals the net force on that little piece of the string. And it depends on how curved the string is. If the string is curved strongly, it'll be accelerating strongly. And so it turns out to be the tension in the string multiplied by the curvature. It's the tension which is pulling that piece of the string downwards. And uh, the textbook will work through this, a detailed argument of this to prove that yes, when you write down Newton's law for the string, it comes out to be exactly in this form. I just sketched an argument of it. So this is based upon Newton's law. Ma equals the net force. What does it tell us? Well, if I compare it against the general wave equation, it tells me how fast the wave travels. If I compare these two, it tells me the value of v squared must be equal to t divided by mu. See, if I rearrange it, I can tell v squared is equal to t over mu, or Newton's law lets you predict how fast the wave pulses move. You have to take the tension in the string, divide it by the mass density of the string, and take the square root. And now we can predict, given a wire under a certain tension and what its mass density is, I can predict how fast the waves will travel down it. Just as an example, if you tighten a guitar string or a piano string, that increases the tension when you turn the knobs. The tension goes up, the waves travel faster on the string, and we'll see that increases the frequency, the pitch of the string. So you crank the knob, increase the tension, the pitch goes up because the speed goes up. Also, the very light strings have very small mass density. Small mass density, note, increases the speed as well. So those very light strings are the high-pitched ones. Okay, so we've looked at general wave pulses and the physics that underlies them, and then we can use that to predict the speed the pulses will move. Now I want to look at the sinusoidal type waves, the ones that have this shape, and write down exactly what their wave function looks like. So notice that it had a wavelength. So it's not just a pulse, it's a repeating set of pulses, and therefore it repeats whenever x advances by lambda, the wavelength. Okay, so let's try to figure out the mathematical wave function then. So at t equals 0, let's suppose this is a sine function at t equals 0. Here's the wavelength. This is, remember, the x-axis, and I'm looking at y as a function of x. There's lambda, the wavelength. And this shape travels, let's say it's a right-moving wave at speed v. What I can do is I'll write down what it looks like at t equals 0. At t equals 0, it's just a sine function. Y equals a sine, a is the amplitude. It's sine of something. It's not just sine of x. X is supposed to repeat, the wave shape is supposed to repeat whenever you advance x by the value lambda. So for example, if I go from x equals 0 to x equals lambda, the shape just repeats itself. That means it has to be sine of 2 pi over lambda times x. That way, if you increase x by lambda, like you replace x with x plus lambda, you just change it to sine of this plus 2 pi. And you know that if you add 2 pi into a sine function, that doesn't change its value at all. So a sinusoidal wave has this wave function. This is only at t equals 0. Of course, I want to know what it is at any time, not necessarily 0. We saw the trick. The trick is the shape moves to the right. And if you want to know what the y value is at some later time, you just have to look back where it was at x minus vt. So all I have to do to figure out what it is at a later time is replace x with x minus vt. So it's 2 pi over lambda, and it's not just x, but x minus vt. Okay, so that describes a sinusoidal wave traveling to the right. Now, of course, it could be cosine as well for another example of a wave, or you could put some phase into it, and it would be something between sine or cosine. Now, we want to abbreviate things here. Obviously, 2 pi divided by lambda is something I want to give its own name. It's called the wave number. Wave number, we call it k. It's by definition 2 pi divided by lambda. It's called the wave number. That doesn't mean it has to be like an integer or something like that. It's just a number that describes what it actually describes is how compact the waves are. You see, if lambda is super small, that's a very, very short wavelength type wave, and it has a very large wave number. Now, the wavelength of a wave it's the peak to peak distance, but it's also how far the wave moves in one period. You see, in the time it takes one piece of the string to go up and down, that's when the wave has advanced a full wavelength. You can tell because as one piece of the string goes all the way down and back again, that's when one full cycle of the wave has passed through. So, in other words, it's just the well-known fact that wavelength is the speed of the wave multiplied by the period of the wave, the period of the vibrations of the wave. This lets me make some simplifications here. It means, for example, that 2 pi times v over lambda is just the same thing as 2 pi divided by the period of the wave, since v over lambda is just going to be 1 over the period, which is what we know as the angular frequency of the vibrations, omega. So it means we can write our wave function in a simpler form, in an abbreviated way. The amplitude times sine kx minus omega t. That's an abbreviated way to write it. K is the wave number. It describes how dense the wave is in space, how closely packed the waves are in space. Omega describes the frequency, how often it repeats in time. If omega is very big, then it repeats very, very often in time. Now, the speed of the wave, so when you write it in this form, k and omega, and by the way, this k, of course, has nothing to do with the spring constant. There's no spring around here at all. There might be a string, which is carrying the wave, but k just has to do with the wavelength of the wave. When you write it in this form with k and omega, that kind of obscures what the speed of the wave is. So it's useful to be able to express it again, the wave speed, to be able to express the speed of the wave in terms of omega and k. So the speed of the wave is the wavelength divided by the period, which is the distance divided by the time. And you can check that this is the same thing as taking omega and dividing it by the wave number k. Omega gives you the 1 over t part, k gives you a 1 over lambda up in the numerator. And so wave speed can be calculated if you know omega and k, the wave number. Next up, some examples.